Welcome back, ladies and gentlemen. Right, so I want to point out that this particular notation where we write EFT.
There's different things. Come and ask questions.
Just an observation with this notation. This is one of those other pieces of mathematical notation that's still getting settled. The notation that your text uses is dvf. So if we look at an example from our text,
One moment, please.
unclear how to test if this is secure, they're just pulling it off. In any case, sorry. So if we look at directional derivatives in text, you'll see them written as d sub vector of f. Oh, sorry. Yeah, so d sub vector of f. So this means the derivative in direction v. Now, in order to explain what the formula of the text is using, I need to tell you about this upside down triangle thingy. So we'll define that. So this is something that we call the gradient of f. And it's defined as follows. So it's the vector of partial derivatives of your function. So it's a vector of partial derivatives of our function. Okay, so in our definition up here, we can see that we have some business involving the partial derivatives of our function. And we notice that we have a dot product, in fact. Right, where we multiply those by the components of our function. Okay, so rewriting things in this new notation involving the gradient, you get gradient f dot v. We pronounce this thing as gradient f. Who's heard of gradient ascent? Has anyone seen that in sort of machine learning contexts? Okay. There's one machine learning guy, that's all right. So gradient descent has the following very neat property. So what's so special about this gradient vector? Well, the first thing is that it lets us do directional derivatives. So that's nice. But it actually has a nice, sort of intrinsically important mathematical property. So recall that when we have a dot product, right, if we dot product two things together, we get cos theta. And so we get the two lengths times the angle between the vectors. Okay? So when we analyze a directional derivative, we can use this property of dot products. So we get the directional derivative is this dot product. Dot products can be broken up as follows. But we know that v is a unit vector. It's of length 1. Right, so this guy has total length 1. We get gradient of f times cos theta. And now, if you're doing sort of a machine learning optimization kind of thing, you often want to make a function grow as fast as possible. Right? You want to, maybe the function represents your revenue for a particular input or something. So you want to make your revenue grow as fast as possible. Now, what that corresponds to is making the derivative in a particular direction grow as fast as possible. So the question comes up, how do we maximize our function? What do we do to make this number as big as possible?
Cough.
Sorry, come again? Mumbling? So how do we make well, we have a choice. We have a choice of direction. Right? So we can pick many directions for v. But the gradient has a fixed length, right? Once we're at a point, we get a gradient vector. This length here is fixed. So what direction will maximize this thing? How big, okay, or to put it this way, how big can cos get?
1.
Yeah, 1, yes, okay. So, to maximize this thing, we make cos equal to 1. What does that say about our vectors now? They're parallel. Yeah, so how do we maximize the derivative in the direction v? We go parallel to gradient. Go parallel to the gradient vector. So this is a really, really, really beautiful thing. This gives us the direction that the function grows the fastest. So just to sort of recap. So we make cos theta in this expression equal to 1. As theta is equal to 0, which implies we go parallel to the gradient vector. So I'd like to take a couple moments to first calculate a directional derivative. We haven't really calculated one yet. Then I want to calculate this approach using gradient vectors. So we'll put together the pieces for calculating such a thing. Okay. So we have a formula that tells us following. So we need the gradient of our function. So we take the derivative in x, put it here, derivative in y, put it here. Okay. Now we multiply things out.
Then we just plug in the value.
Yeah, then we plug in the value. So I want to say, or just to like be explicit, I want to say what this thing is measuring. If you were hiking on this surface, why are you hiking there? Perhaps you're having a nightmare. If you're hiking on this surface and you head in this direction, what this thing measures is the slope of the mountain. Is the mountain going up? Is the mountain going down? Okay, so you've got this surface, you've got a direction. If we think about where this direction is, right, in sort of normal hiking description, this would be northeast. So just graph this very quickly to see what's going on. So here's our surface, and we've got a point. Okay, so there's this little blue dot is our point. Okay. So far, so good. We see the little blue dot. We see the surface. Now, we start at that point and we start hiking. Okay, we start walking along this surface. Okay? And we notice that when we move northeast, right, we are always traveling along that same intersection with the plane. Right? So if we travel northeast, what slope should we experience?
0.
Okay, can I get that in unison?
0.
What slope should we experience?
0.
Yay! Okay. So we plug in our x value and our y value.